Hi, my name is Dan Garcia. I'm a teaching professor at UC Berkeley in computer science, and I'd love to give you an introduction to the beauty and joy of computing. We're part of the CS for All family. On the right, you're seeing the BJC logo, and as part of the CS for All family, one of our goals is to broaden participation in computing to students who normally wouldn't have received computer science. So we're trying to get computer science to all the corners of the globe, and we'll get to that a little bit later. So, lest you think this is only my project, give you a little history. This started, BJC started many, many years ago, 2008, October 26th. I attended a session by Jan Cooney, one of the leaders in the CS for All movement. I mentioned CS for All earlier. And I basically, the writing was on the wall that they were going to create a new AP course. We didn't have a name for it. We were thinking principles might be it, but we hadn't settled on the name. And I ran back to Berkeley to meet with my colleague, Brian Harvey. And I said, Brian, we've got to convert our non-majors course into what I think could be the world's greatest AP computer science principles course. And so we worked on this, and we got some wonderful graduate students. You might know the name Colleen Lewis, who's currently at the University of Illinois. She was a grad student at the time, some other great undergrads, and we basically whiteboarded the project, and we said, how can we take the best parts of our old course, which was taught in Scheme. We take a very functional approach where data is immutable, and the goal isn't to change an array, but to return a new array. So you treat data as if it's frozen, and you can only add things to it, not mutate it. And the computer science is about functions. And we'll get a little bit to that a little later. But the idea was, we love this course. It was in Scheme, which is a text-based language, and we said, could we improve on that? So we looked all around the world, and we found Scratch was the best language, but Scratch, you couldn't make your own functions. So Brian and I got together, and we said, well, what if well, it turns out we found this one, a fork on Scratch, which was version 1.4, 100, again, 14 years ago, and the fork allowed you to write functions, and it was written by an author named Jens Moding. So we said, let's try this. So we actually used, at the time it was called BYOB, Build Your Own Blocks, and Brian and I created this course and launched it in the fall of 2009. And we were chosen as one of the top 5 national pilots. And Tiffany Barnes, you see on the right, Tiffany was another national pilot, and she was teaching in the spring, and 4 of the other instructors were all teaching in the fall. And they were encouraging the instructors to reuse our work. So Tiffany came to Brian and myself, and she said, could I join your team? The course that I want to create is basically the same course that you have already. So could we work together? And I borrow your materials. We said, wonderful. We'd love you to borrow our materials and adopt them the way you wanted to. So she adopted them. She had some game maker and some game design stuff at the end, and we loved it. So we said, let's form a team. So the 3 of us got together, applied for some National Science Foundation fellowships, scholarships to be able to run professional development opportunities for high school teachers. We got the big grant, which was BJC for New York City, which allowed us to bring on a team from EDC, the Educational Development Corporation in Waltham, Massachusetts, June Mark, Paul Goldenberg, Mary Fries, and Salim was working at the EDC at the time. And so we this wonderful team built a version of our existing BJC course at Berkeley, but made it really high school ready. You couldn't just take the Berkeley course and start teaching in high school. That wouldn't be appropriate. We needed to add a lot more scaffolding, a lot more support, a lot more structure, a teacher's guide. We didn't have any of that because we were teaching it ourselves. We added wonderful members of our team, Lauren Mock and Michael Ball, BJC. Jens, again, was the SAP, now works at SAP, but he was the author of BYOB, which became Snap. And Bernat Romagosa has also worked significantly on BJC and helped with that, which is wonderful. Putting some context, again, the reason we all did this was in 2012 when we were thinking about, again, I mentioned we talked in 2008, but even in 2012, the number of students who were taking computer science was very small compared to the other APs, and it was not diverse at all in terms of women and students of color. So we needed to do better. We collectively, as a CS for All family, needed to do better to bring CS to more students. So again, this is some more history of BJC. CS Principles was born. Again, Jan Cooney was a key leader in this by helping that. Wonderful group of folks who put the APCS principles. Lynn Diaz was part of that family, Owen Astrakhan, Amy Briggs, a lot of really wonderful folks who were part of the early CS principles movement. I was fortunate to be chosen to be on the College Board CS Principles Development Committee. So I actually helped build the course and build the first version of the course, where we had a portfolio. And we created the portfolio. Jan called me up and said, "What do you think about a portfolio?" I said, "I love it." So we had a portfolio as part of the assessment that we had. So all this assessment came from those early conversations. Again, CS Principles, a real key piece of it is, how do you get a new course nationwide? Exploring Computer Science is an outstanding course out of LA, but because it was an AP course, they've had to do all that work to get grants and to get to teachers and to get it in all the big cities, and they've done an amazing job, but they didn't kind of have the wind behind them, the sails. They didn't get to ride on the train of the College Board and the AP program to get it into every single school in the country. We try to do that with CS Principles, and I would say BJC is one of the aligned curriculum for that. So again, CS Principles, this is a little bit earlier version. I think it's changed a little bit now, but we had 7 big ideas, 6 computational thinking practices. And actually what was fascinating about it, as we looked at BJC, we were doing all of this. Like I mentioned, there's a portfolio. In BJC, we had a portfolio. We had students doing what we called a create task. We called it their final project, but the students of their own choice. And so there was a big discussion in the early days of CS Principles. Should there be a list? Should there be a list of the projects that students could choose? No list. Should there be a list of languages? No list. Any language, big tent approach, everyone's welcome into the family of CS Principles. That was a fundamental piece of it. Obviously, we had chosen Snap. It wasn't like we at Berkeley let you choose any language. We were choosing Snap, BYOB, which became Snap, and eventually we actually added Python to that. But we all appreciate and all bought into the CS Principles approach, and many people were on the same page, and it was just wonderful that the energy in the national space was so exciting. I mean, many of us had an opportunity to go to the White House, as you know, some of these summits, and it was just amazing seeing all the people, kind of all these educators aligned with trying to have outreach and trying to broaden participation in computing to students normally who hadn't gotten it. So let's talk about BJC specifically. What makes BJC special? Well, it's more programming heavy than most of the others. At some point we had a SIGC session and we all lined up from all, one of the big players, and we all said, how much programming do you do? And we asked for a number. And I think we had like 70 or 80% of our activities were programming activities. We also, again, because the core of it came from our university course, a lot of them, a lot of the courses that were created didn't start from university course. Some of them did, but not all of them did. Because that we had these powerful ideas we were teaching at Berkeley, we wanted to make sure we're in CS Principles. So you think about the things that are required for CS Principles is a set here, but the things that are part of BJC is a larger set. So BJC is much larger than what's required in CS Principles. If some way, said another way, you might think that if you do all 8 units, you're doing all of BJC. We basically had a lot of conversations that, and I'll get to this in a second when we actually show you the example of our curriculum, but recursion is not required by the College Board for APCS Principles. In fact, almost nobody I know of any other curriculum has recursion. We teach it in BJC at the university, and we have it as the things you do after the APCS Principles exam. We want to focus on getting the students, every minute of it is to get them successful for that exam. The moment the exam hits, if you have time after that, there are extra units you can do there. Procedures as data, that's part of abstraction. That's how you hide, it's called Lambda, and it's how it functions as data. Those of you who've seen BJC before know that the idea is you can pass a function into another function. That's a mind-blowing concept, that a function can be a unit of thing that you can drop on your foot, and you can pass this function into another function and do something. It's just really beautiful to highlight the value of abstraction there. We teach concurrency, distributed computing, as is taught in CS Principles, and we believe that because we came from a scheme origin, scheme is the programming language, a Lisp variant, that we have a functional programming paradigm emphasis, meaning it's all about functions that return values, not about functions that do things. We call them commands in Scratch or in Snap, but we talk about reporters that return new values. Again, I mentioned we have a graphical language. This makes coding concepts easier. And we have been teaching at Berkeley, even before CS Principles asked us to teach global impact, we were teaching the social implications of computing and balancing optimism with pessimism. We use this wonderful book, Blown to Bits. It's a free book. It's a PDF. You can buy it, but you can also download the PDF. It's wonderful. So again, we actually, we started from scratch. We literally started from scratch and then built out BYOB. And then I didn't build it. Jens and Brian together collaborated to do that. I just take credit as one of the biggest evangelists, but I haven't put my fingers on the source code. Contributed a couple of libraries and not libraries, but a couple of projects and some other things and some inspiration, but really they're the ones they should get all the credit for Snap. Wonderful language. By the way, at the time it was working. Here's a picture of me showing a demo working in the iPad. Scratch couldn't do that. Scratch was initially, there was a little bit of a competition between Scratch. It's a friendly, we're all friends. We think of, if there's Scratch, we think of ourselves as Scratch Senior in some sense. If there was a Scratch Junior and then the Scratch, we must be Scratch Senior. But Scratch for the early days couldn't run on an iPad or on a phone because it was written in Flash, and we could. So we were very excited to show about that. But we believe that Scratch is amazing. We really want to give Mitch Resnick and his team all the credit they deserve for making an amazing environment, amazing program environment for that. And we're friends with that community. It's wonderful for that. We play well together. This is kind of what you do if you've run out of things to do in the Scratch community. Try Snap and try the Snap community, and you can then there's no ceiling to that. They explicitly make it easy for kids, and they don't want to have functions that return values in Scratch. They decided not to do that. If they had, we would have had a different conversation of what language we chose. But because they didn't, we had to make our own. Here's an example, and it's written in JavaScript. I mentioned in the browser. Here's an example of taking a for loop and actually using it. So how many other languages do you know that if a for loop were not built into the language, you could build it in the language and then use it naturally as if it came down from the mountaintop? So it's wonderful. So most languages can't do that. So this is the front page. I just want to give you a little bit of a curricular flow, give you a web demo of how this works. The website is bjc.edc.org. Again, EDC, Brian, worked with EDC, embedded himself in EDC, lived on the East Coast, worked with EDC, again, in Massachusetts, doing this. Let me do a quickie share and change the screens here and show you what this looks like as I get the right window open. I had it right here, and I need to find it. And it was right here, and I gotta find it. Okay, it moved. There it is. No, there it is. Okay, that's funny. It's not showing a screen. There it is. Okay, that's so funny. It was all white, even though clearly there's text on it. It was an all white picture for you. This is the teacher guide. Let me go to the front page again. I was just playing around for a second. So this is the main page, bjc.edc.org, of our curriculum. You can get there via bjc.berkeley.edu, which talks also about our professional development opportunities we offer and some other things. We have some research and some videos and things. So you click on the curriculum in the middle, and you get a series of units. Units 1 through 5 are what, and then the 2 create task is what you do. That we talked about. They stopped having the explore task be something that was done in the portfolio. But 1 through 5 is all you need, and it covers all of the new updated curriculum, the 2 APCS principles curriculum framework. And then units 6 through 8 focus on extra pieces that are not necessarily there. They're basically our Berkeley curriculum and some extra stuff that used to be there. How computers work used to be, required, but we moved it out there. Fractals and recursion is functional recursion. It's command-based recursion, and unit 8 is functional recursion. Again, APCS principles endorsed. Every time you click on one of these units, you'll see a couple of things. We start at unit 1, lab 1. You get started. You're getting used to the software. You're making a little game where you click on this and moves around randomly. Then there's some conversations and gossip. You're playing with modern art and graphics. So this is a chance to have some fun and make a little pinwheel and make a beautiful pinwheel. And, that's a common activity you do in early Scratch exercises where it's kind of very scratchy in this early unit. We talk about privacy, a little social implications, and then a little idea of event-based programming. Because again, Scratch and Snap are event-based as well as being functional. They're event-based where it's all about, when something happens, trigger something. And again, there's some fun optional projects you can do at the end of that. Let me just go back here. So abstraction is the most powerful idea in computer science, and this is an example of, we really do want to make sure that, and again, it's one of the big ideas in CS principles as well. We were so delighted to see that. So we have a number guessing game, can you guess the number? Well, is it linear? Can you do a binary search? So there's some fun there. We practice on teaching about an abstract data type. We're playing a little bit with a shopping list app. So we created what's called an abstract data type to create a shopping list, and we talk about that. Then we have to do some basics of programming. So this is predicates, conditionals, Boolean values. This is the first time. Here's keep, where you're going to be exploring this block, this gray border means you're taking a function in as input. Keep is like a filtering procedure. It takes a list and then removes the elements that don't satisfy this thing, keeps the elements that do satisfy it from this list. And we introduced new vocabulary for that. So this is the first time we're teaching you and having as part of our core curriculum, having these higher order functions there. We do some more math operations and have some fun with this. And then again, we have computing, social implications computing. We're talking about copyright and fair use and Creative Commons. Then we get a little bit deeper into data structures. Again, this is mostly following what CS Principles curriculum framework requires, but we also had this in Berkeley before that came up. So this is him. So we're talking about complexity. The reason you think about abstraction hides the detail. The reason you write functions is you don't need to know what a function does, you just need to know what the spec of it is. So we do a little wonderful brick wall activity. You play with tic-tac-toe. Again, now we're getting deep into this contact list. Before we had a little bit of that address book. Now we're doing a contact list and creating a contact list in which it's a list of contacts. What's a contact? It's a new data type we just made up, and we talk about that. It's not being very formal, but we're going to quiz you on these things and on the names for these things for a constructor and a selector. That's the kind of thing you do in a college class, the next college class. We're just basically giving you a taste of it. We talk about tic-tac-toe, which we're going to revisit and kind of do a spiral there. And then a little bit of here where we play with some robotics and some AI implications. That's a very rich conversation students have with their instructors when you talk about AI and the implications. And then the future of work. What does it mean when computers might be taking over our jobs? Then they do the create task. Then how the internet works. How the internet works is we used to borrow some videos from code.org. I think they've changed that recently. Little Caesar cipher, some programming. Again, every opportunity we have, we try to have the students program. Rather than read about it, we have them program. Then we have some more, again, social implications of computing, talking about cyberbullying and search engines and censorship. Then again, some more requirements of the CS principles, bits, binary, whole numbers, floating point kind of representation. And that's Unit 4. Then we're almost done. Then algorithms and simulation, again, kind of part of what was required from CS principles. We talk about search algorithms. Again, how do you, how many five-letter words would there be? How about binary search? Could you do this, could we actually search a missing number a little easier, having heuristics in there? Then talk about simulations. We do this in a sense of disease spread, where these things, as they move around, they touch each other and they infect each other when you do this. And then there's a little bit of data, turning data into information, doing some big data analyzing and doing some visualization as well. Now we talk about computability and complexity, unsolvable and decidable problems. We love that part of the class. And then computing in war, powerful. And then we close it up with a big project where the tic-tac-toe, you revisit the tic-tac-toe in a spiral curriculum where we talk about developing a computer game player. And then this is how computers work. This is how to make fractals. This is command-based, where you make a fractal tree. And this is recursive functions, where you're having functions that return values. So let me share again back to that. That's the overview of the curriculum. Hope that was useful to see. And let me go back to the slide deck. And that's the curriculum flow. So we certainly have achieved a little bit of success at the Berkeley level for having so many young women take our course, which has been outstanding. So we were on the front cover of newspapers for having 50% women were taking our course. In fact, we've even got to 63%. So we've shattered the record at Berkeley for the success in terms of outreach to young women for our classes. That's pretty exciting. I want to share that we've also now reached 1,000 teachers and professors. There's 15 schools all around the world that are teaching some variant of BJC and been influenced by us. We're very excited about that. Here's an example of some of our PD we ran back in Berkeley 100 years ago. This is probably realistically 2011 or 12, with wonderful teachers, excited folks. One of the full, a big full room doing that. We brought BJC to Peru, and we've been really excited about some international outreach. And so this is bringing some of the teachers and students of Peru. This is me going to India and bringing BJC to India a couple of years ago. And here's all the teachers in the back row, and some of the facilitators are in the front row. Really excited about that. And thanks to the folks who made that happen. I mentioned that we partnered with EDC thanks to the BJC for NYC grant, and that was bringing BJC to the New York City, which is one of the most diverse with 70% students of color in their school district. So wonderfully diverse. And I'm from New York. So, forget about it over here. It was a wonderful opportunity to come back and bring BJC back to our hometown. And Brian Harvey, my colleague, also was born in New York City. So a lot of East Coast love there. We were so delighted to bring back to there. We created a SPOC, we created a MOOC actually, and then it became a SPOC. A MOOC is a massive open online course, and it became a SPOC, a small private online course, where basically it became this resource on the edX platform. We had 16,000 learners at its peak. We're very excited to reach all these students. We thought this would be the way we would reach all those students who didn't have access to a teacher, but actually, realistically, we weren't reaching them. When it was all done, we were reaching a lot of adults who wanted to find computer science in the world, but we weren't reaching, autodidacts who were ready to just pick up a class. And that's one thing that the MOOC family, in some sense, the MOOC educators have learned, that you just can't have a course out there and have it succeed at the high school level. You have to have a lot of scaffolding. And we were hoping that there'd be some support from a student who might take a MOOC class on one of their free periods, but they weren't really doing that. So that was mostly a bust in terms of what we wanted to have as impact. We've been working on translation into Spanish, BJC traducido al español por Universidad Galileo. Our friends in Guatemala have been helping us with that. So that's a delight, and we're hoping to launch in the summer of 2023 for the first time BJC professional development all in Spanish. The language Snap can be, it's multilingual, so that works in Spanish. Our curriculum is going to be translated by then. It's about halfway, maybe a little bit more than that, translated now as of the summer of 2022. And we imagine that the teachers would be speaking all in Spanish to students in Spanish. So, to our teachers would be presenting to other teachers, and then to the students. So what if a student doesn't know any English at all? Why should they have to use any English words? We should do this. So even though, if you look here, the word report, the word list and item actually have translation. So we need to do a little bit of better job of even translating the pictures within that as well. I would give it a little sense of what we do at Berkeley, how BJC works at UC Berkeley, but basically we cover the same material as the APCS Principles course. The first 10 weeks, we cover all of those units I mentioned. We cover the recursion, we cover higher order functions, we cover parallelism. We have in 10 weeks, just 10 weeks. Well, actually, the 6 projects are over 15 weeks, but we cover all of Snap in 10 weeks, plus the recursion. And then we have almost 4 or 5 weeks at the end, and we teach a gentle introduction to Python. We're basically teaching the same computer science, but in Python. There's really nothing new we're teaching. We do add some object-oriented lectures in there, but really nothing new. We do talk about tree recursion, where recursive reporters walk down and there's more than one call. Just like you saw a fractal tree where there's 2 recursive calls, if you do this on a reporter level, it's a little bit more difficult to trace that for students when they're kind of doing count change. We do count change as an example, we do that. 6 projects, word match, where if I type a word, you tell me how close the word is. So if I type Facebook and the word, I'm guessing it's like a secret word, is fire truck, and you type Facebook, well, the F matched and the K matched and the B matched, but the ones in the middle, so that student has to say that 3 letters matched if you do this. Actually, B doesn't match a T, but so maybe the F and the K match. We'll see. Then there's Mastermind, the classic Mastermind game. This is very much like Wordle, where I have a set of colors, and you're guessing these colors. If those old school folks might remember Mastermind, the game, it's wonderful. We have them code 2048. So we actually do all the graphic GUI event-based stuff, and then just code some blocks. Then they have them do their Explore post. If you remember, the CS Principles used to have an Explore post. We have them do an Explore post. Then they do Python Tetris. So we call it Pytris. So they actually play the game of Tetris, but it's in Python to explore some of the OOP stuff. And again, the create task where they and a group of 2 or 3, just like the create task and the APCS Principles, choose any project they want to over the course of 3 weeks. So they have quite a few, college weeks to do this, unlike the number of hours you're given in high school. They really do have this, and many of them choose games or tutorials, that kind of thing. I want to talk a little bit about the libraries that Snap has. Now getting a little bit to the language itself, less about BJC. You can extend Snap significantly through libraries. If you go under File and Libraries, you get a list of these libraries, and I do encourage you to play with them. These are just wonderful resources. As rather than have 10,000 blocks on the left, we actually hide them, and we hide them under these libraries. And in fact, the new version of Snap allows you to have custom topics, custom tabs. And so now some of these, and the hope is eventually all of them, when you choose, let's say, pixels, there'll be a new pixels tab. And all the new blocks that were loaded with the pixels tab are under the pixels tab, and you'll see that. So we're hoping to do that. I think one of these, I forget which one has that now, but we're hoping to have all of them have that new facility in Snap where there'll be a special tab on the top left and a color too. I also want to mention that in Snap, we have some hidden blocks. This is the design decision made to add a couple of blocks that didn't come built in. Well, as I say, are built into Snap, but they're not really obvious to all of the users of Snap. And the reason we make them hidden, pushback, is that we actually have activities in our professional development like make the greater than or equal block. And rather than kind of, undercut our professional development that's happening worldwide, where people are going around teaching how to use Snap by having them build the greater than or equal block. If you have greater than, you have equal, and you have and you have or, can you figure out how to use and not? How can you figure out how to make the greater than or equal block? Well, if they just, students, but it's right there, it's in the palette. Well, so what we decided to do is actually hide them. So the way you do it is you go up to, if you can see my cursor, you go up to the plus block and you right click and you say relabel. And that relabel lets you rechange. If you have some expression in the two holes and you don't want to change you want to change a plus to a minus or something, or to a times, you don't have to kind of unblock, unconnect them and connect them again. So you can just relabel the plus as something else. But some of the options are not visible in the palette. And that's, the arctangent, the inverse tangent, min and max. And then we also, again, have less than or equal to, not equal to, and greater than or equal to. These are hidden and not available, but I want to make sure everyone who's a teacher knows about these wonderful hidden blocks. And there are actually quite a few hidden menu items. So right click on things a lot and you'll see things that it's a way to kind of reduce the visual complexity of the interface to have these things. Not that that meant that if you read the manual is like a 200-page manual, thanks to Brian Harvey, amazing manual. But if you read this manual, a lot of those are described in the manual. But I want to give some advice. I do have, I think it's one of my last slides. I do have a demo. It's a separate video. I'm going to share that with you with some really fun Snap features, but I want to give you some advice as you're working with students. One of the things I've been really excited about in the last year or two is a movement called A's for All. And it's under the umbrella of grading for equity. The idea is how you grade has equity implications. And what I'm realizing is that I was doing it wrong for 20 years. And what that means is that I was giving students B's, C's, D's, and F's at Berkeley, and I just shouldn't have been. I should have given them more time and asked them, are you willing to put in the effort it takes to get an A? And if they said yes, I will give you then more time. I wasn't doing that. I was saying, the class has to be finished in a semester, and whatever you get is whatever you get, because that's how everyone did it before me. And really the right thing to do is to give the students more time if they're willing to put the time into it. So that's the idea. You're giving students a chance to redo their work. This is part of Carol Dweck's growth mindset. To say you don't know something, you just might not know it yet. There's still more chance for you to know it later, and you're not penalized for learning it later, in that sense. So part of that is how to make this work is you give students second and third and fourth, et cetera, chance exams. You did pretty well, and by the way, if you aced the recursion question, I'm not going to ask you that again. But if you still need some more time to work on, I don't know, functions as data, higher order functions, we'll give you another chance. And then we'll teach you how to, oh, you got that wrong. Let me show you how to do this. And then let you practice, and then come on back and have so multiple chance exams is a very powerful part of the A's for All movement. By the way, the A's for All doesn't mean give free A's out. A's for All means whatever an A was in your own gradebook last year and the year before, that A doesn't change. But the belief is that all students can now get the A, rather than saying, what, A is the top 10%. That's wrong. We don't believe that A is the top 10%. We believe that A means you have some level of proficiency. We call this proficiency-based learning. For many people, we'll call this mastery learning. We like to call it proficiency-based learning. But the idea is whatever an A meant years ago, that's what an A really is. We're not just giving free A's out, but we're going to give every student a chance to get to that A bar. And again, the key is the belief that every student can succeed in computing. And this has a lot of powerful effects on student sense of belonging. I have students who may get a B or a C and say, I guess computing isn't for me. And that's wrong. That's dead wrong. We need to undo that. And we need to give those students more time. If they're willing to put the time into it, give them more time to do that. The analogy we use for A's for All is, if you have a ditch and the goal is to dig, above 9, a ditch that's at least 9 feet deep. If it's bigger than that, that's great. Maybe that's an A+ down there. But if it's at least 9 feet deep, it's there. And after the semester's over, if you only dig it 5 feet deep, well, you tried. Rather than giving them a C and saying only 5 feet, that's a C. You say, are you willing to put more work into it? They say, sure. Well, let me show you how. It's almost like a golf tutor. Let me show you how if you arch your back, do this way, you do this better, and giving them more time to do that. If they're willing to put in the effort and they're willing to have the time, maybe over the summer or maybe, second chance exams. A lot of K-12 teachers are wonderful in leading the charge for ACE for All. It's really about higher ed, people who I'm working with, I need to convince to do this. But, it's very common for a kid to get an essay with marked up and say, hey, you can resubmit it with corrections for full credit. That's the spirit of ACE for All. So try to do this as much as you can in your courses, in our BJC course. If they didn't, there's no reason any students shouldn't get 100% on every single project. You just tell them what's wrong and they go back and fix it. And then if they fix it, then they should get full credit. Second piece of advice I would do, and this is some advice I've been giving to my fellow instructors at Berkeley, is encourage students to find an underground project. Encourage students to like computer science for computer science sake, to just love doing it. And so that, they're idle on a weekend, they might actually enjoy it and create a project and have some friends get together and do that. And let's let that be something that, rather than playing games and playing Minecraft and playing other things, have programming be something that they might do for fun. Their computer science is going to grow exponentially if they are letting that drive what they want to learn. I did this myself. I love game theory. I love Tic-Tac-Toe and board games. So I wanted to write a piece of software to solve that. And I kept working on that and working on it for 20 years. I kept doing it. And I said, I need to learn how to do a network call and how to use graphical interfaces and how to do that. And so how to use databases, all those things I was learning through my own project, driving that. The third piece is Python should be the next language students learn after learning Snap. There's almost universal agreement that among higher educators that APCSA needs to switch out of Java into Python. I think Java is a terrible first language. It's just too verbose. It's a professional language, and many people agree with me. It focuses too much on the OOP details. We kind of came around it wrong. We need to change it to Python and have it not focus on OOP. Let's have it, and not be typed either. That's another piece of it. Let's have untyped languages in the first experience, as Snap is, which is wonderful. And finally, the last advice is encourage, as I encourage my own students to shoot for the moon for graduate school and for getting into internships and going for the Googles and the Apples and the Facebooks of the world. Encourage your students to shoot for the moon and not sell themselves short. And I'm sure you're doing all of that, but just a kind of reminder that it's very easy to know, well, like maybe I'll never get into Berkeley or MIT or that. No, you don't know that unless you apply. You'll never, and the golf analogy, you'll never get in the hole unless you put it past the hole. You have to give it enough power to go, you'll be short every time. So give enough ooch and encourage the students to, and so what if they get, lots of no's, but one or two of them be yeses, and boy, that was great. And they wouldn't have necessarily gotten to that level of school if they didn't shoot for the moon. So I'm done. That's my BJC summary. I tried to give you a little taste. I'll stop the share, but try to give you a little taste of the experience, the history of BJC, the curriculum overview, kind of the reasons why we do some of the things we do, how we play with other curriculum. And again, there's a second video, which is some wonderful Snap demos and some fun activities there. So I hope this was helpful. Thank you for being part of the CS Principles family. Thank you for choosing BJC. Continue to share the love of computing with your students and broadening participation in computing. Thanks so much. Good to talk to you.